In 12.2, we're going to continue our look at quadratic functions. We're going to be looking more at the quadratic functions that have this form of y equals ax squared plus bx plus c, and seeing what the effect of having this extra b term in the middle, which we haven't seen before, see what effect that has on the graph. And what we'll find out is that the line of x equals negative b over 2a gives us our axis of symmetry, which means we know that this is going to be a vertical line. Remember, that axis of symmetry is the vertical line that kind of cuts right down through the center of the graph. So the x-coordinate of our vertex, now instead of being at 0 and some value like we had before, the x-coordinate of the vertex is now going to be at that negative b over 2a value. The other thing we'll notice is that if we substitute 0 in for x into our function, then we'll get y equals c, which means that the y-intercept of the graph is always going to be that value of c, that constant at the end of the function. So between knowing the y-intercept and being able to find this axis of symmetry, that will aid us in graphing these new forms, or this standard form of these quadratic functions. So if we look at this first example, we want to graph the function y equals x squared minus 6x plus 4. So that the first thing we're going to look at is we're going to figure out where is the axis of symmetry. And we're going to use that form of x equals opposite of b over 2a. So if we plug in, we can see here is our b value. It's the coefficient on the linear term, on the x term. So we have the opposite of negative 6 divided by 2. Where is our a value? Our a is the coefficient of x squared, which in this case is 1. So when we take the opposite of negative 6, that would give us a positive 6 divided by 2, gives us 3. So our axis of symmetry is the line x equals 3. We must write the axis of symmetry in that form because it is a vertical line. It is not just the number 3, it is the line x equals 3. So now that we know that our vertex is going to have the x-coordinate of 3, and we need to figure out the y. Well, the y-coordinate comes from taking that value of negative b over 2a and plugging it back into the function for x. So we'd have y equals 3 squared minus 6 times 3 plus 4. So that gives us 9 minus 18 plus 4. This will give us negative 9 plus 4, which gives us a y of negative 5. So our vertex is going to be at 3, negative 5, right down in here. Remember that our constant c, that's our y-intercept. So 4 means that our y-intercept will be at the point 0, 4. Up here. So using our axis of symmetry, we know that x equals 3 is the line of our axis of symmetry. So this point 0, 4 is 3 units to the left, means we will also have a point 3 units to the right. So we would also have this point out here at 6, 4. And here is our vertex down here at 3, negative 5. So we really need to just find one more set of points. Okay. So if we think about an xy table, okay, I'm going to let x be 1. So I'd have 1 squared minus 6 times 1, which would give me negative 5, plus 4, which would give me a negative 1 for y. So I have 1, negative 1, and I would use the symmetry to move over 2 units to the right. And that allows us to complete our graph. So when we're graphing these functions, we're going to use the axis of symmetry, the y-intercept along with the symmetric property, okay, and then choosing another x value or using the graphing calculator to come up with another ordered pair. We want to make sure that we've got the vertex and we'd like at least 2 points on each side. Okay. So let's look at the next graph. Graph the function and label the axis of symmetry and the vertex. So we want to graph this function of negative x squared plus 4x minus 2. So we're going to start out with negative b, or opposite of b, over 2a to find our axis of symmetry. Well, b is 4, so I have negative 4 over 2, and the a this time is negative 1. Remember, a is the coefficient on the x squared. So we've got our a is negative 1, our b is 4, and our c is negative 2. We're going to use all of those values in some capacity. So this gives us negative 4 over negative 2, which is positive 2, which means our axis of symmetry is the line x equals 2. So to find our vertex, we know that the x is going to be 2, and then we will replace all of the x's with 2 and figure out what the y-coordinate is. Well, 2 squared is 4, so this becomes negative 4 plus 8 minus 2. Well, negative 4 plus 8 is 4, minus 2 gives me 2. So there is our vertex. So our vertex is going to be at the point 2, 2, and our axis of symmetry will be this line here at x equals 2. So when we label it, we draw it underneath there so that we've labeled what that line is. And our vertex is here at 2, positive 2. Where is our y-intercept? That's one of the other key parts of the graph that we'll identify. Remember, our y-intercept is the constant, the c value. So our y-intercept is at 0, negative 2. Okay? And I can use the symmetry, that's 2 units to the left. So I would also have a point 2 units to the right at 4, negative 2. So I'm just going to be in need of one more set of points. Okay, so I'm going to let x equal negative 1. So I'd have y equals the opposite of negative 1 squared plus 4 times negative 1 minus 2. Well, negative 1 squared is 1, but that's the opposite, so it becomes minus 1. Minus 4 minus 2 gives me negative 5, negative 7. So at negative 1, I'm at negative 7, and that is 1, 2, 3 units to the left. So I would go 1, 2, 3 units to the right. Okay, so I have 5, negative 7, and I also have negative 1, negative 7 as my points. And I would be able to sketch in, not the greatest sketch, kind of missed that point up there, but I can sketch in my parabola. And notice here that my vertex this time is a maximum because it is a high point as compared to the previous graph, which had a low point, making it a minimum. Okay. So let's try another one. See if you can get this on your own before I go through and do the problem. So we're going to start with opposite of b over 2a, which would give me negative 8 over 2 times negative 2. Negative 8 divided by negative 4 is positive 2. So my axis of symmetry is the line x equals 2. My vertex is at 2 something. So to figure that out, I'm going to replace all my x's with 2. So that gives me 4 times negative 2, which is negative 8, plus 16, and plus 9. So that's going to be 17. So our vertex is at 217, which is a little bit off of the graph that I have here. So we'll just kind of improvise a little bit. And we'll plot 217. We'll just say that it's right up here. I know that the graph is going to open down. Okay. Clean that up a little bit. 217. I know my graph is going to open down because my a value is a negative. I know that my y-intercept is here at my c value at 0, 9. Okay. I know that my axis of symmetry is coming through x equals 2. So there's my axis of symmetry. Now my y-intercept was 2 units to the left, so I'm going to have another point 2 units to the right at 4, 9. And here's the point 0, 9. And I just need another set of values. Okay. So again, I'm going to let x equal -1, or I'm going to go to the graphing calculator and look for another set of points in the table function. So -2 times -1 squared, 8 times -1, and plus 9. So that's going to give me -2 minus 8 plus 9. So -10 plus 9 is 1. So I know that -1, 1 is a point, which is 1, 2, 3 units to the left. So 1, 2, 3 units to the right would be 5, +1. And I would have my sketch, okay, a little narrower than some of the other graphs because of that integer of -2 out front. And again, I can see that my vertex is a maximum. We've got our axis of symmetry, we've got our vertex labeled, and we've got our 2 points on either side of the axis. So let's see how this stuff translates into a motion problem. Before we had the falling object, this -16 t squared plus c. I think we used plus h in class. Well, now we're going to look at what happens when instead of dropping something, it's given some sort of a velocity. It's launched, or it's shot, or it's thrown. So now we'll have this middle term of vt, which is that b value. Okay. So here's our problem. During the halftime of a basketball game, a slingshot launches t-shirts at the crowd, has an upward velocity of 72 feet per second. There's our v. It is caught 35 feet above the court. How long will it take the t-shirt to reach its maximum height? Okay. What is the maximum height? What is the range of the function that models the height of the t-shirt over time? Okay. So here's the things we're going to be looking at. So let's see how this problem is going to relate to this projectile motion equation. So here's our function, h equals -16 t squared plus 72t plus 5. That gives us the t-shirt's height after t seconds. Okay. The t squared is negative, so we know the parabola opens down and our vertex is going to be a maximum. Okay. So how long will it take the t-shirt to reach its maximum height? Well, where's the maximum height going to occur? The maximum is going to occur at the vertex. So we simply have to find the vertex. So we're going to use our x equals -b over 2a, which gives us -72 over 2 times -16. So we've got -72 divided by -32, which is approximately 2.25 seconds. So that's how long it takes to reach its maximum height, because remember that x is now taking place of the t in the vertex, and the x value is the time. So 2.25 seconds is a maximum height. So the next question says, what is the maximum height? Well, the maximum height would be the h, which would be the y value of our vertex. So 2.25, that was the x value. So now we're going to need to plug in the 2.25 for t, and then simplify and solve for h. Forgot to replace our t value there. This t value here should be our 2.25. And when we do that, we'll get 86 feet as our maximum height. Okay. So it asks, what is the range of the function? Okay. Well, the range, the lowest value we had was where it started, okay, which was at 5 feet off the ground. Okay. And the highest value, and then that came from the diagram in the previous picture, and the highest value was the maximum height of 80 feet. So our range is between 5 and 86. So 5 is less than or equal to h is less than or equal to 86. So remember, we talked about how sometimes the real world problems put some different restrictions on our domains and our ranges. And here's another example of that, where it's not just that the range is less than or equal to 86, but it's only going between 5 feet and 86 feet, the lowest point and the highest point. Okay, so one more problem. And I'd like you to try this one on your own. It's in a similar fashion to the last one. A baseball is thrown into the air with an upward velocity of 30 feet per second. Okay, so there's our v. And the function is given as negative 16t squared plus 30t plus 6. How long will it take the ball to reach its maximum height? Well, again, remember that when we're looking at these problems, we're graphing height versus time. We're throwing the ball up, it's coming back down. So its maximum height is occurring at the vertex at some time, and then its maximum height. So we need to look for that axis of symmetry. So if we think about our negative b over 2a, that would be negative 30 over 2 times negative 16. And that would give us, so when we finish our calculations here, we've got negative 30 divided by 2 times negative 16 gives us 0.9375 seconds. So just a little bit less than 1 second to reach its maximum height. So to figure out what that maximum height is, we're going to plug that 0.9375 in for t into our function and figure out what the height is at that time. So when we finish our calculations, we find that that height comes out to be approximately 20 feet. The last question says, what is the range of the function? So again, this is one of those cases where we're not just going y is greater than or equal to or less than or equal to some value. Okay? The maximum height is 20, so we know that 20 is the largest value. But what is the smallest? Where did it start? Well, where it starts is it started 6 feet off the ground when it was thrown. So in reality, if we were to look at just a kind of a rough sketch of our graph, it was thrown from 6 feet in the air and then it came down here. So we're not really getting the full parabola. So our range is between 6 and 20. Okay? So we'll do some more work with these problems involving this axis of symmetry tomorrow in class.